Hello, this is Tommy. Welcome back to Genomics. In today's video, I'm going to show you how to do the most common operations for genomic data sets, which is do the intersection of two genomic intervals. So in the end, I will show you how to use a command line tool called bedtools to do such operations, and also compare it with the R solution using the genomic ranges package. So make sure you stick to the end. So if you ask me what's the most common problem you need to solve when dealing with genomic data, for me it was the overlapping of two genomic interval sets. Okay, we know genomic data usually represents in a linear way, so the chromosome name, start and end. So we use it to define, for example, a region in a genome. It can be a peak from ChIP-seq data, the location of a gene, chromosome name, exon 1, intron 1, exon 2. Those are all genomic intervals, right, in the genome. Or a DNA methylation site is a single point, or a mutation core or a duplication region in cancer cells. So when I started to learn programming 12 years ago in a wet lab, so my task was to find where a set of peaks binds to genes. So those peaks are from ChIP-seq experiments. So to solve this, we have two dummy files like here. So a peak file with chromosome, start, end, and you can have additional columns for annotation purposes. And then you have another file which tells you where are the genes or where are the promoters of those genes. So you have also chromosome, start, end, and then the gene name, for example. So the task is easy, right? So find overlaps of those two files. So in fact, you can actually eyeball it and see like peak 1 binds to gene 1 and peak 3 binds to gene 3, right? But however, when you have thousands of peaks and thousands of genes, how do you do that programmatically? So as a beginner 12 years ago, I didn't know much, so I actually wrote a Python script which read in those two files simultaneously and loop over line by line and compare the coordinates, right? For two regions to overlap, there are actually 4 such conditions, right? And that's actually a lot of conditions to compare, right? So you have to compare the start and end. So we can actually look at the opposite side. There are only 2 conditions where 2 regions that do not overlap. So you have start 1 is greater than end 2, or start 2 greater than end 1. So you can negate this condition and to get the condition that 2 regions overlap. So essentially in programming, so if not those 2 conditions, then those 2 regions overlap. So my naive methods, brute force methods works, but it's not efficient. So later, actually, I got to know a data structure called interval tree, which makes this type of operation much faster and efficient. So in 2010, bedtools was published. So this is a command line tool that is designed to do such operations really easily. So with a single command called bedtools intersect, you can accomplish what I did with my Python script. Okay, so if you go to the documentation of the bedtools, so there are many commands actually available from bedtools, but one of the most commonly used one is called bedtool intersect. So here, so if you click this, it will tell you what does this command do for you. Okay, so you have 2 sets of genomic intervals, A and B here. So if you just do naively A intersect B, so it will give you the intersections, okay? But if you use A intersect B hyphen WA, it will tell you the original regions, genomic intervals in A that is overlapping with B, okay? Okay, let me actually show you how to do that on command line. Okay. So I will also show you how to do that with R using the GenomicRanges package. So in my original blog post, actually I introduced many more concepts and also methods for genomic ranges. You can read that. So I will have the link for this blog in the description of this video. Okay, but to do this, actually we are going to download the two files. Okay, so go to this geo session, and then let's download two ChIP-seq files from HIF1 alpha and HIF2 alpha chip sequencing experiments. Okay, so if you click those two links, and then you come here and you can download this peaks.bet.gz file. Okay, click either one of them, you'll be downloading those two files. Okay, so I have already downloaded them. So let's go here. So those two files. So you will see those two files, they ends with the .bat. So bat is a format. So minimally it requires 3 columns: chromosome, start, and end. We can take a look of the file. If I use the head command, and essentially you have the chromosome, start, end. This is the peak ID, and this is just the value of that peak, or maybe the intensity or the p value, log 10 p value, okay, minus log 10 p value. Okay, so to do that, so by the way, I have already installed bedtools. In one of my previous videos, I actually show you how to use Conda to install bedtools. So make sure you check that video if you don't know how to do that. But I have already installed bedtools. So if you do bedtools intersect, it will show you all the available parameters or the flags that you can use. Okay. So to do this, but before we do that, I always want to look at how many peaks in each file, right? So just what count -L, only count the line of the file. So you have 1,496 in this file, and 1,417 in this file. Okay, and so take a look. So one of them is HIF1 alpha, and the other one is HIF2 alpha. Okay. So to look at the intersection of those two genomic sets, interval sets, we can use bedtools intersect file A GSM, for example. Let's use the HIF1 alpha as the A sets. So it will be 8, and -B will be 8, 0. Okay. So now we need to use this -WA flag, and it will tell you, it will give you all the original regions in A. Okay. WA, and if you type enter, it will show you all the regions in A that overlaps with B. Okay, and we can save that in the new file. Okay, but actually you can check how many of such regions, right? Okay, actually we made a mistake, so we're using the same file here. So let's see. So let's redo it. Bedtools, and let's remove the HIF1, and then redo the bedtools. Intersect A will be this one, dash B will be this one, and then we can look at how many peaks overlap. Okay, there are 94 regions in A that overlaps with B. Okay, we can actually switch those two as well. So bedtools intersect dash A and dash B, and see how many of B that overlap with A. Also 94. But actually there's a little trick here. So you have to do, so if you look at the first several rows, it's like this. But if you do sort and unique and do count again, it's only 93. The reason is that in this file, there are actually 2 peaks overlap with the same peak in B. So by default, actually, bedtools will actually have the duplicates there. So if you do sort and unique, you will get the unique original regions in this file. Okay, actually we can verify that using GenomicRanges. Okay, let's go back to R here. So, okay, we can use in R, we use library rtrack layer to read those bed files. Okay, if we read this, and this is the HIF1 alpha peaks, and this is the HIF2 peaks. Then see how many of them. So it will tell you 1,496, and this is 1,417, right? This is the same as what we see here. Okay, it's the same number. Okay, and how many of them are overlap? So in GenomicRanges, you can use subset by overlaps. If you do that, it will show you there are 93. Okay, remember what we see here? We have 93. But if you switch the position, okay, of those 2 arguments, HIF2 first and HIF1 later, and you will see there are 94. Okay, and this is what we see here, 94. That shows you actually they produce exactly the same number. Okay, and what people usually do is, okay, what's the percentage, for example, then you calculate, okay, 93 divided by divided by this, or 94 divided by this. So you just calculate the percentage of peaks that is overlapping with the other sets. Okay, this is just a very preliminary introduction for genomic interval analysis. Make sure you check the bedtools tutorial. There are many other functions or command line tools that you want to use. And at the same time, make sure you go to my blog post and learn how to use GenomicRanges to do many other very useful operations for genomic intervals. Okay, that's it for today. Make sure you subscribe to the video, and I will see you next time. Happy learning.